So good morning guys. Today we will see the examples related to your one-dimensional steady-state heat conduction as well as heat convection. Okay. In previous lectures or in previous examples we have only studied about heat conduction problems. Now we will see here the heat conduction as well as heat convection, means finite elemental procedure applied to heat convection with heat convection. Okay. So we have actually derived this equation. Okay, for this heat conduction with heat convection. Okay, so first term here it is nothing but your conductive stiffness matrix. Second term it is nothing but your convective stiffness matrix. This is your boundary condition or force vector due to heat conduction. This is the force vector due to heat generation, and this is the force vector due to heat convection. Okay, so these are the terms we need to take into account while solving the heat conduction with heat convection problems. Okay, now we will see one example related to your heat conduction with heat convection problem. Okay, so we will see one example here. So as we know that this is the equation. By using this equation we are going to solve this heat conduction with convection problem. So we will see now one example. So here in this example it is given that a cylindrical field, that is one of the several in a small exchange device. Okay, the left end of the field is subjected to the constant temperature of 180 degrees Celsius. Okay, here it is given that the field it is given here and its left end of the field is subjected to the constant temperature of 180 degrees Celsius. Okay, so left end it is maintained as constant temperature of 180 degrees Celsius. Then right end of the field is in contact with chilled water bath maintained at constant temperature of 40 degrees Celsius. Okay, right end it is maintained at a chilled water bath. Okay, it is maintained at a chilled water bath of temperature of this water. It is given equal to 40 degrees Celsius. 40 degrees Celsius. Okay, the exterior surface of the field is in contact with moving air at 72 degrees Celsius. Okay, the exterior surface of the field it is in contact with the moving air. It is in contact with the moving air. Okay, this is your moving air of temperature of air is given equal to 72 degrees Celsius. Right end it is maintained in the bath of a water bath, which is maintained at 40 degrees Celsius. This exterior of the field it is maintained at a temperature of 72 degrees Celsius. Okay, the physical data it is given like that. The diameter of the field it is given equal to 0.5 meter. Then length it is given equal to 4 meter. Then kx is given equal to thermal conductivity is given equal to 120 watt per meter degree Celsius. Then h of air means the convective heat coefficient or heat coefficient due to convection of air it is given equal to 50 watt per meter square, and heat coefficient due to convection for water it is given equal to 100 watt per meter square degree Celsius. Okay, then use 4 equal length elements to find out the temperature distribution within the field. Okay, here the question is what? Use 4 equal length elements to find out the temperature distribution within the element. Okay, so as we know that all the data it is given here, like the left end of the field. Here total length of this field it is given equal to 4 meter. This is equal to 4 meter. Then the left end it is maintained at 180 degrees Celsius. Right end it is maintained in a water bath at temperature 40 degrees Celsius. Then exterior of the surface it is maintained or it is in contact with the moving air with temperature 72 degrees Celsius. Then the convective heat coefficient for air, it is given equal to 50 watt per meter square degree Celsius, and convective heat coefficient for water, it is given equal to 100 watt per meter square degree Celsius. Then the thermal conductivity of this fin material, it is given equal to 120 watt per meter degree Celsius. Okay. Also the diameter of the fin is given, and find out the temperature distribution within the fin element by using 4 elements. Okay. So use 4 elements to find out the temperature distribution within the element. So it means for this first node, this is your T1, for this second node, this is your T2, for this third node, this temperature is your T3, fourth node, this is your T4, and for fifth node, this is your T5. Okay, so here the temperature of this water is given, not T5 is given, but the left end is maintained at 180 degrees Celsius. It means the temperature T1 it is equal to 180 degrees Celsius, it is given because this surface is maintained at 180 degrees Celsius, and this surface is in contact with the water which has temperature equal to 40 degrees Celsius. So T5 it is not equal to TW. TW is different, T5 is different. Okay, so these are the given data. Now we need to find out the temperature distribution. So final aim is what our to find out T1, T2, T3, T4 and T5 values. Okay, so how to find out T1 to T5 values? So as we know that this problem is related to your heat conduction with heat convection. Okay, so in previous week we have studied that this exterior surface of the fin is insulated. In that case, only heat conduction will takes place. Okay, so as we know that if this surface is insulated, it means what? The heat convection is restricted here. Only heat conduction will takes place through this fin. But here, this exterior surface it is exposed to the surrounding medium, that is air medium. So in that case, the heat loss will take place by the mode of heat convection. Okay, so we need to take account this heat loss due to heat convection also. So we need to take account these both losses, means due to conduction as well as due to convection. So as we know that for this case we need we have one equation which is nothing but this is the equation Kx into A into this matrix T1 T2 plus HPAL by 6 into this matrix into T1 T2 is equal to area times this is conduction vector, this is generation vector, and this is your convection boundary condition. Okay, so we need to apply this equation to this fin problem. Okay, so how to apply this equation? So first we need to find out these two matrices for each element. Okay, why? Because heat conduction is takes place in this direction as well as for this element heat convection is also takes place. Okay, so it means what? We need to take into account these both effects, that is heat conduction as well as heat convection. So we need to find out first convective as well as conductive stiffness matrix for this first element. Then similarly we need to find out convective and conductive stiffness matrix for each element, that is for 4 elements we need to find out conductive and convective stiffness matrix. Then we need to add these 4 elemental stiffness matrix with the help of their node connectivity to find out the global stiffness matrix. If we find out the global stiffness matrix, then we will find out the further your boundary conditions. Okay, so first we need to find out the conductive as well as convective stiffness matrix. So for this element, okay, if we take this element in a free body diagram, then it will become the, so this will become first element, second element, third element and fourth element. Okay, so first one is temperature T1, it is given equal to 180 degrees Celsius. Second is your T2, third is your T3, this is your T4 and this is your T5, and around this there is a water which has a temperature of 40 degrees Celsius. Okay, Kx is equal to Kx into A divided by N. So this is the free body diagram. So here, this is first node, this is second, this is third, this is fourth, and this is fifth. Okay, and also the temperature of air, it is given equal to 72 degrees Celsius. Okay, so with the help of this first and second matrix, we need to find out combine the stiffness matrix for this first element only. Okay, here length is equal to 1 meter for each element. Here all the parameters are same for each element because area it is same, that is 5 by 4 d square. Then perimeter is also same, that is 5d for each element. So we need to find out first area for each element, perimeter for each element. So you will get area equal to, if you find out the area, then you will get area equal to 0.1963 meters square. 0.1963 meters square, which is same for all elements. Then perimeter it is equal to 1.57 meter. 1.57 meter, which is also same for each element. Okay, so it means what? We need to find out this matrix, that is we need to find out first Kx into A divided by L in bracket 1 minus 1 minus 1 1. Okay, so you will get this Kx is equal to 120. So it is given equal to 120. So 120 into area is equal to 0.1963 divided by length is equal to 1 inch into 1 minus 1 minus 1 1. Okay, so you will get this Kx into A by L, which is equal to, okay, this value you will get first is equal to, by putting all these values you will get 23.52. So you will get 23.52 minus 23.52 minus 23.52, 23.52. Okay. Similarly, find out this convective stiffness matrix. For this case, find out here H. It is H of air. It will become H of this air. Okay. Because this is your air medium. So we need to find out with the help of H air. So H air. So what is the value of H air? H air is equal to 50. So this will become 50 into P, perimeter is equal to 1.57 into area is equal to 0.1963 into L is equal to 1 divided by 6. So you will get this value equal to, this value it is equal to 2.57. This is equal to 2.57 in bracket 2112. Okay, so in this way you will get this value as 2.57 in bracket 211. Okay, and for this case the vector is same, that is T1 and T2. Okay, so we need to combine these both effects and finally we will get into one matrix, as this matrix is equal to, if we add both these values, if we multiply 2.57 into 2, you will get this matrix 2 by 2. This is nothing but a 2 by 2 matrix, and for both matrix the temperature vector is same, so you can add easily. So by adding this matrix you will get one combined matrix and its value is equal to 28.66 minus 20.95 minus 20.95, 28.66. Okay. So this is the combined vector due to your conduction as well as convection effect. Okay. So as for each element the given data is same, so we will get for each element this combined stiffness matrix. Okay, and its position is in between node 1 and node 2. For first element it is in between node 1 and node 2. Okay, so now we need to find out the global stiffness matrix. Okay, as we know that this is our elemental combined stiffness matrix due to conduction and convection. Now we need to find out the global stiffness matrix. Okay, so as there are four nodes, four elements, 1, 2, 3, 4, and there are 5 nodes. So combined global stiffness matrix will become of order 5 by 5. So it will become like 1, 2, 3, 4 and 5. So this will become like that. PA is equal to 750. 1, 2, 3, 4 and 5. Okay, so for first position, first elemental combined elemental stiffness matrix we need to place between 1 and 2 connectivity. So 28.66 minus 20.95 minus 20.95, 28.66. Then second connectivity of the second elemental stiffness matrix is in between node 2 and 3. So between node 2 and 3, node 2 and 3. So this is the connectivity. So plus 28.66 minus 20.95 minus 20.95, 28.66. Similarly, third is nothing but 28.66 minus 20.95 minus 20.95, 28.66. Then again last one, 28.66 minus 20.95 minus 20.95, 28.66. In this way you can add it global. So 28.66, it is nothing but 57.32. So 57.32. 57.32, and remaining elements are equal to 0. Okay, in this way you will get this elemental stiffness, global stiffness matrix for this 4 elemental fin. Okay, so now next is what? Now we need to find out the boundary conditions, or we need to simplify the RHS of this equation. Okay, so this is your heat generation, this is the load vector due to heat generation source. As we know that in this case heat generation source is absent, or it is not mentioned in this example. There is a heat source, so this will become equal to 0. Now this will become equal to, for this first node there must be a Q in, and for fifth node there is a heat loss. Now this heat loss is due to this convection only. Here heat loss is taken place this convection, and we know that the heat loss due to convection is given by H delta T. Okay, now here H is nothing but H of the water. So H of the water it is given equal to, H of the water it is given equal to 100. So 100 into delta T. So sorry, it is given equal to 100 So this Q5 heat loss due to convection, because at node 5 the heat loss is taken due to the convection, because this fifth node is in surrounding with this water medium which is at temperature equal to 40 degrees Celsius. So there is a heat loss due to convection, and we know that the heat loss due to convection is given equal to H delta T. So H is equal to 100 into delta T. Delta T is nothing but the difference between surface temperature and water temperature. So this will become 100 in bracket T5 minus T water is equal to 40. Okay, because H of water is given equal to 100. So this will become equal to my 100 times T5 minus 40. Okay, or simply you can say H times T5 minus 40, because H is equal to 100. So instead of this we can write, here, okay, you can write here for first element Q in, second for second node 0, 0, 0, and for last node it is equal to minus, this is area times minus area times H T5 minus 40. Okay, so this is your force vector due to the heat conduction. For first node it is conducting inside, and for last node it is going outside, means the heat loss is taken place due to the convection. That's why we have taken here H delta T into this area, and negative sign is there because this is a heat loss. That's why we are taking negative sign. Now the last boundary condition is whatever due to the heat convection. Now see here, due to heat convection we need to find out this boundary condition. We know that for each element there is this element is surrounded by this air. Similarly, second element is surrounded by air. So for first element we need to find out the heat loss due to convection by this equation. So for first element it is in between node 1 and node 2. So this will become equal to H of air into P into T of air into L divided by 2. Similarly, H of air, P, T of air into L divided by 2. This is for first and this is for first element. So this value, by putting all the values, you will get this is equal to 2.826. 2.826 actually. This is equal to actually 10 raised to power 3 into 2.826. 10 raised to power 3 into 2.826. 2.826. If you simplify this by putting all the values, you will get 10 raised to power 3 into 2.826, 2.826. Okay, this is for element 1. Similarly, for element 2, this will become between 2 and 3. That is, between 2 and 3 it will become 10 raised to power 3 into 2.826, 2.826. Similarly, this is for first and second, this is for second and third. Then again it will become for third and fourth, same, 10 raised to power 3, 2.826 and 2.826. And finally again for element 4, 10 raised to power 3 into 2.826, 2.826. Okay, so in this way you can determine. Now we need to add this combined, we need to add this elemental effect combined to get the combined effect due to the heat convection. So how to add? So this will become equal to 1, 2. This will become equal to, so here we will write T1, T2, T3, T4 and T5. So similarly, as we have done all this like that, so this will actually become 2826, 2826. So here only we need to write down first. Now here we will write down first this A times Q in 0, 0, 0 and minus A into H T5 minus 4T plus this will become equal to, for first element 2826, 2826, then again 2826, 2826 plus 2826, 2826 plus 2826 and finally it will become 2826. So in this way you will get this load vector related to the heat convection. So now solve the 5/5 equation here on here. Okay, so as we know that, so here we will add effect. So this will become equal to actually instead of area is equal to 0.196 actually 0.196. Area is equal to 0.196 into Q in, and this area is equal to 0.196 into 100 into this T5 minus 40. Okay, so if we add this will become plus 2826 plus this will become equal to 5652, 5652. This will become 5652. This will again become 5652 and this will become 36112. Actually this will become equal to 19.6 into T5 minus 40 plus this 2826. Okay. Here we have combined both effects, that is conduction as well as convection. So it will become 0.196 into Q in plus 2826, 5652, 5652, 5652 and 19.6 because this area into minus actually. This is minus because heat loss is there, so we need to take it as minus. Minus 19.6 into T5 minus 40 plus 2826. So combinedly it will become, okay, only we will solve this, it will become minus 19.6 T5 minus plus 19.6 into 4T plus 2826. Okay, so combined it will become minus 19.6 into T5, it will just simplify, minus into minus it will become plus, so minus 19.6 into 4T, minus 19.6 into 4T plus 2826, and if we just calculate this value, you will get equal to 3611.2. 3611.2. So if instead of this you can write this value, so this will become minus 19.6 into T5 plus 3611.2. Okay, so here all terms, here only Q in is unknown value, T5 it is also an unknown value, but for this, because this T5 we can add this T5 into this fifth equation, because if we write down this fifth equation it will become 0 into T1, 0 into T2, 0 into T3, this into T4 plus this into T5. So we need to add this minus 19.6 into T5, this effect on this side. Okay, because this equation will become minus 20.95 T4 plus 28.66 T5 is equal to minus 19.6 T5 plus T6 11. Okay, so we can add this to this value. So minus 20.95 T4 plus this will become equal to 48.29 T5 is equal to 3611. And now we can write this equation here only. So this value is same. So instead of this value, it will become 48.29. 48.29, and on RHS side, this will become only 3611.2. So this will become 3611.2. Okay, so in this way we have just simplified, because on RHS side T5 is there, so we need to add this T5 on LHS side, so this will become 48.29 T5. Now we can solve by using our penalty method, that is this Q in is unknown, so we need to eliminate this first row as well as first column. So first row as well as first column. Okay, now we need to check whether the effect of this 20 minus 20.95 is there or not. So minus 20.95 into T1, but T1 is given. T1 is equal to 180 degrees Celsius. Okay, so if we write down this equation, we will get minus 20.95 into 180 here only. So this is nothing but this equation, because we need to make this element equal to 0. If we need to make this element equal to 0, so it will become here equal to 0, and this minus 20.95 minus 20.95 into 180, this will become, or this will goes to this RHS. Okay, so this will become 0, and this is transferred to the RHS side because of this T1 effect, and this will become equal to plus 20.95 into 180. Okay, so this is the, we need to transfer this effect to the RHS side. So we will get these 4 equations now, because this effect is transferred. Why we are transferring this effect? Because for this value there is a temperature value T1 is equal to given 180 degrees Celsius. Now if we look for these 3 equations, this is 0 into this, 0 into this, 0 into this, so there is no effect for this first level. But for this case there is an effect due to this temperature T1. So we need to transfer this value on RHS side. So you will get this value. And if we now solve this 4x4 matrix by using Gauss elimination method, you will get the temperature values T2, T3, T4 and T5. Okay, so how to solve Gauss elimination? So first we need to make, so this is your final matrix. We need to solve this matrix by using Gauss elimination. Means we need to make the elements which are below to the diagonal elements equal to 0. So we need to make this equal to 0, this equal to 0, similarly this equal to 0 by using the row and column transformation. Okay, so if we solve this by using the Gauss elimination method, you will get the values like T2 is equal to, first you will get the T5 value, then you will get the T4 value, then you will get T3 value, and finally you will get T3 value. Okay, so solve this by using the Gauss elimination method, you will get these values as T5 is equal to 90.79 degrees Celsius, T4 is equal to 97.23 degrees Celsius, T3 is equal to 111.02 degrees Celsius, and T2 is equal to 136.16 degrees Celsius. Okay. Then by putting all the values of T2, T1 to T5 in first equation, you will get this Q in. So Q in is nothing but equal to 26 Watt per meter. Okay, so in this way you can solve for temperature distribution by using this Gauss elimination method. Okay, so here we will stop, or we will conclude our lecture. So try to solve this matrix by using Gauss elimination method. You will get these 4 values. Okay, so here we will conclude our lecture. Thank you.